My stomach hurts. But this coffee was totally fine on the first day. Oof, bitter and flat. Gross. What has happened to it? Days of sitting out. Is this even healthy? Oh wait, I'm a chemist. I could just measure it. I need a team. Now that you've met our team, let's take a step back and look at the core principles behind our measurements. Here is a pipe, which is usually made from stainless steel. Both ends are narrowed, and we pack this closed pipe with a solid material called the stationary face. Now we have a chromatographic column. To the beginning of the column, a bottle of liquid is attached, which is the mobile face. Somehow, we push the liquid through the column, namely by a pump. The column is getting filled with the mobile face, and the red bar is the front line of the liquid. Before repeating this procedure, we apply a one-way opening to the inlet of the column. We have this blue-colored chemical compound called the analyte. It has a certain ability to bind to the stationary face. This phenomena is called adsorption. We inject the analyte into the inlet of the column, where it adsorbs to the stationary face. While pushing through the liquid, the compound is carried by it. The analyte moves slower in the column than the liquid because of adsorption. Adsorption here is similar to the brake in cars. The stronger it is, the slower the analyte moves. More precisely, the stronger it is retained. The front line of the liquid is called the solvent front, and the analyte is a retained compound. A simple example may help you understand this process. Imagine a common, lazy river water ride in your favorite water park. The water flows, and people are swept by it. Now, if someone puts his feet at the bottom similarly to adsorption, it slows down the sweeping. Now, we are going to simulate how it works in real-life applications, but first, we have to introduce some modifications. We apply a detector at the outlet of the column, which is going to provide a response over time. When an analyte passes by the detector, a signal is produced. In real conditions, a sample usually contains many different analytes. All of these adsorb to the stationary phase to a different extent, so their retention is different. The analytes are together within the sample, therefore they are introduced together to the column. During elution by the mobile phase, the difference in adsorption properties forces the analytes to separate from each other. They pass by the detector at different times, producing the signals similarly distributed along the time axis. In the detector response curve, the first arriving compound gives the first signal, and the other signals correspond to the order of arrival. The signals are unique and have many properties. But the most important is that they are peak-shaped. This curve is called a chromatogram. The area under a peak is proportional to the concentration of the corresponding analyte in the sample. Twice the concentration results in twice the peak area.
Can we brew coffee already?
Yes, but we are going to do it in a professional way. We measure everything, the water, coffee, even the temperature. Brewing is done in a well-defined time interval. We measure the mass of coffee brews. Add ethanol and place it into the centrifuge. All we have to do now is to prepare all the samples to the measurement, filter, acidify, and dilute.
When we finished with the measurements, we just simply evaluate our data.
Astro, no. What you know about rolling down in the deep? When your brain goes numb, you can call that mental freeze.
I think you pushed a little far. Let me explain on a simple example. Here is a dataset of different concentrations and the corresponding signals. We create a diagram from these, which is the so-called calibration curve. We estimate the signal response by a linear equation. In unknown, real samples, we calculate the concentration of an analyte just from the signal using a linear formula. We repeat this calculation to all analytes in all samples, and we get how the concentration of each analyte change in overaged coffee brews.
The concept of our project was to monitor changes in the chemical profile over time in still coffee. The relevance likely stems from a common Middle Eastern European habit, namely that elderly people often brew multiple portions and continue drinking them over several days, a practice that also occurs among younger generations. This consumption habit is associated with imbalance of the digestive system. The components contributing to the intensity and complexity of bitterness are molecules constructed from smaller parts. These compounds are called chlorogenic acids, and the smaller molecular parts are mainly caffeic acid and quinic acid. Quinic acid is a center part to which multiple caffeic acid molecules can be attached. These chlorogenic acids degrade over time due to oxygen and light exposure. Temporary compound 5-caffeoylquinic acid is produced in which only one caffeic acid is attached. During breakdown, caffeic acid is released. It gives higher acidity character to coffee. Summarizing sensory changes during the breakdown of chlorogenic acids, 5-caffeoylquinic and caffeic acids are released. By this process, the bitterness complexity decreases and the intensity increases as well as acidity.
We have two theories based on measurements and sensoric experience. The first is chlorogenic acid breakdown as discussed before, which was measured through the concentration changes of 5-caffeoylquinic acid. However, the measurements implied an underlying mechanism which released some compounds into coffee samples just until a certain time. After this time, their concentration didn't increase significantly. This process is associated with carrier molecules such as lipids and other aroma components. The analytes bind to these carrier molecules, and when it decomposes upon oxygen and light exposure, it releases the bound analytes, so we are going to measure it as an excess concentration. The significance of this is rancidity, which is caused by the carrier metabolites. Consumption of rancid products can cause many health issues. Significant quality loss starts after the first 24 hours, therefore we suggest you to consume your coffee maximum 1 day after brewing. We hope you learned something new today, and thank you for watching. And also, thank you to everyone who contributed to this project.